The next topic we are going to be dealing with in this chapter, dealing with equations of chemical reactions, is what we call double displacement reactions. Very similar to single displacement reactions, only now instead of one ion kicking another one out, we have two ions kicking out the other like ion. So this is a double switch, if you will. In order to do this, we have to take a look at the charges of all four components, like we did last time with the single displacement reactions. We had to deal with all four, or all three ions in that case. So you are going to need your polyatomic ion chart, and you're going to need your periodic chart. I have both of mine ready to rock and roll. Okay? Now, you start over here. Copper. Copper is a transition metal. It's in that middle 10 right here. So we can't do that just yet. We will be able to, but we need to go to the negative polyatomic ion that is with it, the sulfate ion, or SO4. So we find SO4 on here, and we find that the charge for this is -2. Therefore, if that's -2, then copper has to be what? Well, it's got to make sure that the two add up to 0. So if this is -2, then this is going to be +2. We come over here to the sodium, Na. Na is a group 1A metal, therefore it has a charge of +1. And the carbonate, the CO3, is in the polyatomic ion chart. Carbonate has a charge of -2. Okay, so now we're going to do exactly what we did last time. We're going to switch ions around, only instead of one getting kicked out being by itself, it's just going to join the other ion. In other words, we have, and I'm going to take the positive approach because I'm a positive kind of guy. So the +2 and the -1 are going to switch places. Now, when you do this, you don't take the numbers that are not normally found with it. So the 2 of the sodium may or may not be found over here, but we don't bring it right away. We have to make sure that the charges required to be balanced and to use the 2 for that. So the Na and the C are going to switch places. So we're going to have Na going with the SO4, and we're going to have the Cu going with the CuCO3. So the copper goes with the carbonate. Okay, now we need to make sure that the charges are balanced. So we go and put in our charges. Sodium's +1, sulfate's -2, copper's +2, carbonate is -2. Well, right away we see that that's the correct formula. That is indeed going to be 0. This is not added to 0, so it looks like the 2 that we had here is going to come up again to balance the charges. It doesn't always work that way, so be careful that just because there's a 2 there doesn't always mean it's going to be a 2 here. It does sometimes, a lot of times it doesn't. So we put the 2 there because +1 times 2 plus -2 equals 0. And that's what we want. Now the next thing we need to do is to check for phases. And there's 2 things going to happen in a double displacement reaction, and I'm going to include a video of a double displacement reaction for you to look at so you can see what happens here. What happens here is that one of them is going to turn out to be aqueous and the other is going to turn out to be a solid. You're going to have a water solution. The word aqueous means dissolved in water. And so we're going to have one of them that's going to stay dissolved in water. We're not going to see it. But the other one is going to precipitate out, is what we call it. A solid quickly appears like a rapid snowstorm hit the middle of your beaker with inside the water. It's pretty dramatic. So you get one of these is a solid, the other is going to be an aqueous solution. So for those of you at your home doing the remote thing, this is the list of ions that you need to be familiar with to know anytime you have those ions in your compound, it's going to be aqueous. All right, so, and if you have 2 ions in there and neither one is found on there, then it's going to be a solid. But if only one of these appears on it, then it's going to be aqueous. These automatically make the compound that they are bound to aqueous, completely soluble in water. So let's go back up here. So sodium sulfate. Well, sodium, well, first of all, you don't see sulfate up here, so that's not going to cause it to be aqueous. But sodium is a group 1 metal ion. There it is right there. And the group 1 metal ions will cause the compound to be soluble in water. So we're going to put an AQ in parentheses right here. Now, because this is a double distillation reaction that we know will occur, we know right away that this is going to be solid, but let's prove it here. Is there a Cu up there? No. Is there a CO3 up there? No. So we know that that's going to be solid, but we didn't have to go through that because in the reaction we see that a solid does appear, and if this is not the solid, then the other one has to be the solid. Okay, now we balance the equation. So, since this is rather spread out, I'm just going to go ahead and put a line right here, and this is going to be on the left-hand side. So we got copper with 1. Now, we're not going to split up sulfur and oxygen. We're going to treat it like it's its own element. So SO4, we got 1 of them. Na, we got 2 of them. And CO3, we have 1. So we come over here. Na, we have 2. SO4, we have 1. Copper, we have 1. And CO3, we have 1. And if you look, the same ions have the same numbers. This is already balanced, so we don't have to do anything special to that. That is the end of our process, and this is our answer right here, without the charges on there. Okay? All right. So, keep referring back and forth. I'll talk about this, but I'm not going to keep going back and forth to it. But you may want to keep it handy just as we go through this so you can understand what I'm doing here. Okay, we'll do this reaction here, or this equation of a reaction. So we need to find the ions in each individual part. So, in this case, K is a metal in group 1A, so that's positive 1. SO3 is on the polyatomic ion chart, and it's called a sulfite. It has a charge of -2. And it makes sense because 2 times 1 is 2, and 2 plus -2 equals 0. So life is good. Mercury, transition metal. We can't find the charge yet. We have to go to the negative ion. When you look at NO3, NO3 is -1 on the polyatomic ion chart. We have 2 of them. We have a total charge of -2, which means mercury has to be what? 2. So this is 2 positive. A positive 2 either way. Alright, so that means then that the K and the Hg are going to change places. But we're not going to take the 2. Now notice the NO3 has a 2 with it in parentheses. That's not part of the NO3. So we don't include that as well. We may have to do that depending on what the charges are of the new compounds, but we aren't going to automatically put it there, okay? So K is going to go with the NO3. We have some phase there, which we'll talk about in just a little bit. And the Hg is going to go with the SO3. And it has some phase that we're going to figure out in just a little bit. So now we're going to re-put all the charges on to make sure that this is the correct formula for each of these compounds. So K is +1, NO3 is -1, Hg is +2, and sulfite is -2. Well, look at that. Charge is already added to 0 both compounds. We don't have to do anything to that. So now what we need to do is figure out the phases. Well, let's start with KNO3. K is a group 1 metal. NO3 is one of the ions also listed. So this is really soluble in water. You're not going to get this to precipitate out, so this is going to be aqueous, and that means that this is going to be a solid. Okay, now we need to balance it. So now we're going to put our line in there. We have K, there's two of them. We got SO3, there's one. We got HG, which is one. And we got NO3, and it looks like we got two of them there. So now we come over here. K is 1, NO3 is 1, there's just one of them. The 3 means it's 3 oxygens, but there's 1 NO3. HG, there's 1. And SO3, we just have 1. There's no parenthesis or number around it. So that's good. So now we check to see if it's balanced. Well, K is 2, K is 1. NO3 is 2, and NO3 is 1. So that's definitely not balanced. So if let's start with the K's here. If I need 2 K's over here on the right-hand side of the arrow, then I need to put a 2 there. So I'll put some 2 right there. But because NO3 is with that compound, that NO3 also has to be doubled, and lo and behold, we balance it just like that. And there is your complete balanced equation for the double displacement reaction of K2SO3 and HGNO3 2. Let's do one more, a little more involved than that.